Welcome. Settle in, get comfortable, close your eyes, and prepare yourself for a philosophical journey. Tonight, we won't be counting sheep. Instead, we'll be contemplating the very nature of reality itself. What if I told you that everything around you, the stars in the sky, the trees outside your window, even you yourself, obeys not just the laws of physics, but also the fundamental laws of information? What if our entire, immense universe, with all its galaxies and nebulae, is actually behaving like a gigantic, unimaginably complex computer? This idea might sound like the plot of a science fiction film, yet today it stands as one of the most intriguing hypotheses at the cutting edge of science. In this lecture, designed specifically for your rest and deep sleep, we will calmly and systematically explore why this notion has so captivated the minds of modern scientists. We will dive into a world where matter and energy yield primacy to information, and reality is fundamentally composed of tiny binary bits. Prepare to discover why the universe itself might just be the greatest programmer of all. Before we delve into the modern theories, let's take a brief journey into the past, because the idea of a computational universe is far from new. Its roots run deep in the history of thought. As far back as the 17th century, the great philosopher and mathematician Gottfried Leibniz, one of the creators of the binary system upon which all modern computers operate, contemplated that reality could be described through the language of logic and symbols. He envisioned a universal language capable of expressing every conceivable truth. But the idea truly began to take physical shape in the 20th century with the invention of the first electronic computers. One of the key pioneers was the German engineer Konrad Zuse. As early as 1945, isolated during the final days of the Second World War, he began to hypothesize that the universe itself might be the result of a cellular automaton, a simple computational system. He even wrote the book Calculating Space, suggesting that the laws of physics could be the result of simple rules operating on a discrete or interrupted grid. But perhaps the most famous aphorism, which became the motto for this entire concept, belongs to the distinguished 20th century physicist John Archibald Wheeler. He succinctly summarized the essence of the theory, it from bit. Wheeler proposed that information is the most fundamental entity in our world, not particles, not fields, not energy, but information itself, the elemental yes or no answers, the 0 or the 1. Every particle, every interaction, in his view, is a manifestation of information. This simple yet profound idea became the starting point for an entire field of science that we will now explore. So, let's start with a fundamental question. What do the universe and a computer actually have in common? At first glance, the answer seems to be nothing at all. A computer is a device made of silicon and metal created by humans. The universe is an immense space filled with stars and galaxies, but if we look deeper, we see a striking similarity in their operating principles. At its core, a computer is an information processing machine. It takes input data, applies a specific set of rules, an algorithm, and produces an output. For example, you type the letter A on the keyboard. The computer receives the signal, processes it according to its built-in algorithm, and displays the symbol A on the screen. Now let's turn our attention to the universe. In essence, it processes information too. The state of the universe at any given moment, for instance, the position and velocity of all particles, can be considered the input data. The laws of physics, such as the law of universal gravitation or the laws of electrodynamics, serve as the algorithms. These laws take the current state of the universe and calculate what it will be at the next moment in time. A planet moves along its orbit not chaotically but in strict adherence to the algorithm we call the law of gravity. Light propagates according to specific rules. Chemical reactions happen in a predictable manner. It all resembles a gigantic, continuous computation. The universe is constantly calculating its own future based on its present state. This analogy is the foundation of the computational universe hypothesis. Proponents of this view suggest that if something behaves exactly like a computer, processing information according to algorithms, then perhaps, at the most fundamental level, it actually is a computer. This isn't just a clever metaphor. It is an attempt to find a new language to describe reality, a language of information and computation which may prove to be deeper and more universal than the traditional language of matter and energy we are accustomed to. To truly grasp the idea that the entire universe might be a giant computer, we first need to clarify a single, crucial concept: information. In everyday life, we usually think of information as knowledge, news reports, text in a book, or data stored on a flash drive. But in physics, this concept carries a far deeper, more fundamental meaning. At its core, information is simply what allows us to distinguish one state from another. Imagine a coin. It can land either heads up or tails up. Since these two states are distinct, the coin holds one bit of information. A bit is the minimal basic unit of information, the answer to a yes, no question, true, false, or represented by a 0 or a 1. Now imagine that reality itself, at its deepest level, is composed entirely of these bits. Every elementary particle, every quantum of space, essentially stores a specific amount of information about its properties, its position, momentum, spin, and charge. When particles interact, they are fundamentally exchanging information. A physical process, such as the collision of two electrons, can be viewed as a computational process where the data about the electrons' initial states is transformed into information about their final states. This idea that information is primary completely transforms our perception of the world. Historically, physicists believed that the fundamental building blocks of the cosmos were matter and energy. Information was merely a property that described the state of that matter, but the concept known as it from bit flips this entire perspective on its head. It suggests that matter and energy themselves are secondary. They are merely manifestations, or, if you prefer, the result of processing a more fundamental entity: information. Consider a character in a video game. While the character appears to be composed of pixels on a screen, in reality, they are just a complex sequence of ones and zeros stored in the computer's memory. To that character, the pixels are reality. To us, they are just the visualization of information. In the same way, our universe may simply be a grand-scale manifestation of some fundamental underlying informational code. If we view the universe as a computer, it must operate on either analog or digital principles. But what exactly distinguishes the two? An analog computer works with continuous values. Think about old vinyl records. The groove etched into the surface is a continuous line that perfectly mirrors the sound wave's shape. Or consider an hourglass, where the sand flows in a single, uninterrupted stream. Classical physics, the physics of Newton and Einstein, is fundamentally analog. It assumes that space, time, and energy can take any value, no matter how tiny or fractional. You can always find a third point between any 2 points in space and another moment between any 2 moments in time. A digital computer, conversely, deals with discrete or discontinuous values. It operates entirely on zeros and ones. All information within it, whether music, images, or text, is ultimately broken down into a finite number of these elementary bits. The picture you see on your monitor is made up of a finite number of pixels, each having a specific color. A music file consists of a finite number of samples which describe the sound's volume at precise moments in time. So what about our universe? For a long time, it was universally assumed to be analog, but in the early 20th century, a revolution occurred with the advent of quantum mechanics, and quantum mechanics brought with it the radical idea of discreteness. It turned out that at the most fundamental level, many physical quantities cannot be continuous. They exist only in separate packets, or quanta. For example, light energy is emitted and absorbed only in specific packets, photons. An electron in an atom can only exist at specific energy levels, like steps on a staircase, and cannot be found anywhere in between. This discovery provided the first strong and compelling argument that our universe might actually be digital at its deepest level. If energy is quantized, why wouldn't space and time be quantized as well? This profound question forms the very foundation of the concept of digital physics. The idea that space and time might not be smooth and continuous, but instead composed of the tiniest indivisible pixels, is one of the most compelling concepts in modern physics. If the universe functions like a giant digital computer, then its screen must have a fundamental resolution limit. This implies the existence of a minimal possible length and a minimal possible duration of time. Such fundamental units indeed exist in theoretical physics. They are known as the Planck length and the Planck time. The Planck length is an unbelievably small quantity, roughly 10 to the minus 35th meters, 10 to the power of minus 35 meters. To truly grasp this scale, consider an atom and then picture the entire observable universe. The size of an atom relates to the size of the universe almost exactly as the Planck length relates to the size of that atom. This defines the fundamental limit of precision with which we can determine the location of anything. It is theorized that at scales smaller than this, the very concept of space ceases to have meaning. Similarly, Planck time is defined as the time it takes for light to traverse the Planck length. This duration is approximately 10 to the minus 43rd seconds. This is the shortest possible instant, the ultimate tick of the cosmic processor. No physical process can occur faster than this interval, so what actually happens at these Planck scales? We don't know for certain. We currently lack the technology to observe reality at this profound level. But theories suggest that at this point, space-time ceases to be smooth. It becomes foamy, grainy, resembling a turbulent, boiling structure of constantly emerging and vanishing virtual particles. It is composed of these fundamental pixels. If these ideas hold true, it provides direct evidence for the digital nature of our reality. Every movement, every change in the universe is essentially the switching of states among these space-time pixels, just like pixels changing on a computer screen to create the illusion of smooth motion. Now let's pivot to one of the most bizarre and counterintuitive ideas we have. Despite its strangeness, it actually fits perfectly into the concept of a computational universe. This is the holographic principle. It was first proposed by physicists Gerard 't Hooft and Leonard Susskind during their study of black holes. The core idea is this: everything that occurs within any given volume of space can be completely described by information encoded on that volume's outer boundary. Picture a standard hologram like those found on credit cards or souvenir items. It's a flat, two-dimensional image, but when viewed from the correct angle, it creates the perfect illusion of a three-dimensional object. Crucially, all the information about that 3D object is somehow encoded onto that 2D surface. The holographic principle suggests that a similar mechanism might apply to our entire universe. We perceive the world as three-dimensional. We experience length, width, and height. But what if that perception is merely an illusion? What if all the data describing our 3D universe is actually encoded on a distant, two-dimensional boundary surrounding us, acting like a colossal cosmic horizon? It implies that we, with all our galaxies, stars, and planets, might be nothing more than a holographic projection of this underlying information. This idea sounds like pure science fiction, yet it rests on serious theoretical foundations rooted in black hole physics and string theory. For instance, it helps resolve long-standing paradoxes concerning information that falls into a black hole. And most importantly, it once again places information above all else. If our entire reality is a hologram, then the fundamental underlying entity is not the three-dimensional space we inhabit, but the two-dimensional information matrix that projects it. This provides yet another powerful argument that the universe, fundamentally, operates as an information processor. Black holes are arguably the most mysterious and extreme objects in the universe, but when viewed through the lens of informational physics, they are much more than just cosmic monsters. They are powerful information storage units and processors. Let's dive into why that is. According to classical theory, anything that crosses a black hole's event horizon is lost to us forever. The event horizon is the point of no return. Not even light can escape its grasp. It would seem that any information carried by the matter falling into the hole, whether it's a book or an entire starship, is instantly destroyed. But this creates a massive problem for physics. One of the fundamental laws of nature states that information cannot be destroyed. It can change form or become inaccessible, but it cannot vanish without a trace. This dilemma, known as the black hole information paradox, baffled physicists for decades. The proposed solution, championed by scientists including Stephen Hawking, is closely tied to the holographic principle. It turns out that information doesn't disappear inside the black hole at all. Instead, it seems to be imprinted or encoded onto its event horizon. Furthermore, research established that the maximum amount of information that can be contained within any region of space is proportional not to its volume, as we might intuitively expect, but to the area of its surface. And this limit, known as the Bekenstein bound, is precisely met by black holes themselves. A black hole is, therefore, the most efficient information storage system allowed by the laws of physics. It absorbs matter and energy, and all the relevant information about what it swallowed is preserved on its surface boundary. Then, through the process of what we call Hawking radiation, the black hole very slowly evaporates, returning that information back into the universe in a coded form. Thus, black holes are revealed to us not as destroyers, but as gigantic cosmic hard drives and processors that recycle matter and energy into pure information. If the universe is a computer, what operating system is it running? And what program is currently launched? One of the most fascinating answers to this question was proposed by scientist and entrepreneur Stephen Wolfram in his monumental book, A New Kind of Science. Wolfram suggested that the incredible complexity we see all around us might be rooted in extremely simple rules, similar to the rules that govern something called cellular automata. What exactly is a cellular automaton? Imagine a grid like a chessboard. Each cell on this board can exist in one of several states, for example, being black or white. Next, we define a very simple rule that determines the cell's color in the next generation based only on the color of its immediate neighbors. For example, the rule might state, if a cell has exactly one black neighbor, it becomes black, otherwise it turns white. And that's it. We start this automaton with some initial configuration, and it begins to evolve step by step, generation after generation, following that single, simple rule. You might think that such primitive rules couldn't possibly generate anything interesting, but Wolfram proved that this is definitively not the case. He investigated a massive number of these systems and found that even the simplest rules are capable of generating incredibly complex and unpredictable behavior. Some cellular automata produce ordered, repeating patterns. Others create seemingly random, chaotic structures. But the most amazing finding is that some of them generate structures that look complex and meaningful, resembling living organisms or intricate snowflakes. They demonstrate what is known as emergent behavior, where complexity arises from simplicity without any complicated blueprint or master design. This mirrors exactly what we observe in nature. Highly complex structures like galaxies, snowflakes, and living organisms all appear as the result of relatively simple physical laws. Stephen Wolfram's core idea is that our entire universe might fundamentally be a giant cellular automaton. Space isn't just empty void, it's a grid, or perhaps a highly complex graph, not necessarily uniform. Elementary particles and their interactions, therefore, are simply the results of a very simple, fundamental program executing on this spatial structure. The physical laws we consider so complex, general relativity, quantum mechanics, the Standard Model, Wolfram argues, aren't fundamental at all. They are merely emergent properties, that is, macro-level behaviors, of this deep, underlying computational system. Think about the weather. We know the underlying principles are relatively simple laws governing the motion of air molecules, but trying to predict the path of a hurricane purely based on the motion of individual molecules, that's impossible. A hurricane's behavior is an emergent property of that massive system. In the same way, the laws of physics could simply be the macroscopic manifestation of a microscopic universal computation. This hypothesis leads to several fascinating consequences. First, it suggests that there might be a single, perhaps incredibly short, and simple program that generates the entire complexity of our universe. Finding this program of the universe is exactly what Wolfram and his team are currently focused on. Secondly, it offers an explanation for why certain phenomena appear complex and unpredictable. Wolfram calls this computational irreducibility. It means there is no shortcut to knowing the outcome of a complex system. You can't just plug numbers into a formula and jump straight to the answer. The only way to find out what happens next is to simulate the system step by step. And if our universe is indeed a computationally irreducible system, it means its future is fundamentally unpredictable. We can't fast-forward it, we can only experience it, tick by tick, cycle by cycle of the cosmic processor. Let's continue building on the analogy of the universe as a computer. Any computer program, no matter how complex, adheres to certain internal rules and constraints. For instance, in a video game, a character cannot pass through a wall because that is how the game engine is programmed. There are specific invariants, quantities, that remain unchanged. Now let's look at our universe. It also possesses fundamental conservation laws. The most well-known are the law of conservation of energy, the law of conservation of momentum, and the law of conservation of angular momentum. The law of conservation of energy states that energy cannot be created from nothing or destroyed into nothing. It can only be converted from one form to another. For example, the chemical energy in a battery turns into electrical energy, and then into light and heat energy in a flashlight. But the total amount of energy in a closed system remains constant. Similarly, the total momentum, the quantity of motion, of a system of bodies remains unchanged unless external forces act upon it. Within the hypothesis of a computing universe, these conservation laws take on a new perspective. They can be viewed as the fundamental rules or invariants of the universal computer program. These are the conditions hardwired into the code of reality which cannot be violated. They ensure the stability and predictability of our world. If energy were not conserved, the world would be a chaotic and unpredictable place where objects could arbitrarily appear and vanish. Conservation laws are the guarantee that the calculation performed by the universe is consistent and logical. Interestingly, in physics, these laws are intimately connected to the fundamental symmetries of space and time. For instance, the conservation of energy is a direct consequence of the fact that the laws of physics do not change over time, and the conservation of momentum is a consequence of them being the same everywhere in space. From the perspective of the computer analogy, this means the universe's source code is universal and does not depend on where or when it is being executed. Every computer is bound by a fundamental limitation, the speed of its processor. A CPU can execute only a finite number of operations per second, and it simply cannot operate any faster than that ceiling. This speed dictates the maximum rate at which information can be processed and transmitted within the system. Does our universe possess a similar constraint? Indeed it does, and it's a limit known to everyone. That limit is the speed of light in a vacuum. According to Einstein's special theory of relativity, nothing with mass can ever exceed the speed of light. Crucially, this means that no information, no cause and effect signal can propagate faster than this ultimate velocity. The speed of light represents the absolute cosmic speed limit. But why light? When viewed through the lens of the informational paradigm, the answer is remarkably elegant. The speed of light is more than just the velocity at which photons travel. It is the fundamental rate at which information spreads throughout the very fabric of space-time. It is, metaphorically speaking, the maximum clock rate of the universal processor. Imagine the pixels of space-time we have discussed. The information concerning the state of one pixel cannot be instantly transmitted to its neighbor. Instead, it takes precisely one tick of the cosmic clock, a duration known as the Planck time. The speed of light is, in fact, the ratio of Planck length to Planck time. This defines the ultimate rate at which the state of the universal grid refreshes. This fundamental limit carries profound consequences, chiefly because it defines the very structure of causality in our world. Events can only influence one another if there is enough time for a light signal to travel between them. This limitation gives rise to the concept of the light cone for every event, the region of spacetime it can influence in the future, and the region that could have influenced it in the past. Anything outside of this cone is entirely, causally disconnected. Therefore, the absolute speed limit we observe in physical reality can be interpreted as a fundamental constraint on the rate of information processing within our computational universe. Previously, our discussions about the universe often relied on analogies with classical computers, which fundamentally operate using binary bits, zeros and ones. But around the turn of the 21st century, a new and vastly more powerful computational concept emerged: quantum computing. Strikingly, the world of quantum mechanics, the realm of atoms and elementary particles, turned out to be remarkably similar to the world of a quantum computer. What is the key difference? A classical bit must be either a 0 or a 1. A quantum bit, or qubit, due to the principle of superposition, can be both 0 and 1 simultaneously, existing in every possible combination between those two states. It is only at the moment of measurement that it collapses or selects one definite state. This is often likened to a spinning coin, which is both heads and tails until it lands. This unique property allows quantum computers to process a massive amount of information in parallel. A machine with just a few dozen qubits can perform calculations that are beyond the reach of even the most powerful classical supercomputers. Here is the crucial point. The elementary particles in our universe behave exactly like qubits. An electron, until we measure its spin, exists in a superposition of both spin-up and spin-down states. A photon is in a superposition of all possible paths until it hits a detector. Fundamentally, all of quantum mechanics describes the evolution of these very superpositions. Physicist Seth Lloyd calculated that if we consider every elementary particle to be an information carrier, the universe has, since the Big Bang, performed approximately 10 to the power of 120 elementary logical operations. This is a truly colossal number. This strongly suggests that if the universe is a computer, it is not a classical machine but a quantum one. Every process occurring within it at a fundamental level is, in essence, a quantum computation. And the familiar classical world we inhabit, the world of definite positions and speeds, is merely the result of a measurement, or decoherence, where a massive quantum superposition collapses into one particular observable state. Quantum entanglement stands out as one of the strangest and most counterintuitive phenomena in all of quantum mechanics. Einstein famously dubbed it spooky action at a distance. Here's the core idea. We can create a pair of particles, such as two photons, whose states remain interconnected regardless of the distance separating them. For instance, if we entangle them by polarization, the moment one photon is measured as having vertical polarization, the other instantly assumes horizontal polarization and vice versa. What's truly astonishing is that this link persists even if we separate these particles across the entire galaxy. The instant we measure the polarization of the first photon, we instantaneously know the polarization of the second. The information appears to be transmitted immediately, faster than the speed of light. While this seems to violate the principle of causality, the idea we previously discussed, it actually doesn't. Entanglement cannot be used to transmit meaningful information faster than light. We cannot force the first photon into a specific state to send a message to the second one. The result of the initial measurement is always random. We only learn about the correlation after the fact. So how do we explain this instantaneous correlation? From the perspective of the computational universe hypothesis, entanglement can be viewed as a unique, non-local connection operating within the code of reality. It's like having two variables in a computer program that are hardwired together. A change in one instantly reflects in the other, regardless of where they are stored in the computer's memory. Entangled particles are not two independent entities. They are a single system described by one common wave function, a unified object within the program. Spatial distance simply doesn't matter for this connection. This suggests that our intuitive notion of space as something that separates objects might be incomplete. On a deeper, informational level, everything in the universe may be far more tightly linked than we realize. The quantum world holds another profound enigma, famously known as the measurement problem. According to the equations of quantum mechanics, a quantum system, like an electron, exists in multiple states simultaneously or in superposition until the moment we measure it. This state is described by the wave function, which evolves smoothly and predictably over time. But the moment we try to measure any property of the system, say its position, something strange occurs. The wave function instantaneously collapses, and the system randomly snaps into one of the possible states. The electron, which was essentially smeared out across all of space, suddenly appears at one specific point. Why and how does this collapse happen? What is so fundamentally unique about the act of measurement? This remains one of the deepest unresolved questions in physics. There are numerous interpretations. The Copenhagen interpretation, for instance, simply postulates that measurement is a fundamental, irreducible process that cannot be described by the very same quantum equations. In contrast, the many worlds interpretation suggests there is no actual collapse. Rather, at the moment of measurement, the universe splits into countless parallel worlds, each realizing one of the possible outcomes. Shifting to the computational hypothesis, however, allows us to view the measurement problem from a completely new perspective. The act of measurement becomes the moment when the universe as computer must compute and output a specific, definite result. Prior to measurement, the system remains in a state of uncertainty, essentially a set of probabilities, much like a computer storing information as a probabilistic distribution. Measurement is a query to the system, forcing it to finalize the calculation and deliver an unambiguous answer. Why is the outcome random? Perhaps this connects to the concept of computational irreducibility that Wolfram discussed, or perhaps the universe's underlying algorithm has a fundamental element of randomness built in, a cosmic random number generator, if you will. Regardless, this transition from quantum uncertainty to classical certainty can be viewed as a crucial stage in the ongoing computational process that defines our reality. All this discussion about the universe operating like a computer inevitably brings us to one of the most thrilling and unsettling ideas: the simulation hypothesis. If our universe functions like a machine, if it is governed by algorithms and fundamentally composed of information bits, couldn't it be artificial? Couldn't we all be characters within an extremely advanced computer simulation launched by some hyper-advanced civilization? This idea, famously popularized by the movie The Matrix, actually rests upon serious philosophical and scientific foundations. The most recognized argument supporting this claim was articulated by philosopher Nick Bostrom. His thought experiment, known as the simulation argument, is built upon three core assumptions, or postulates. The first states civilizations almost certainly go extinct before reaching the technological maturity required to create realistic ancestor simulations. The second, if civilizations do reach that maturity, they are, for some reason, uninterested in running ancestor simulations. And the third, we are almost certainly living in a computer simulation. Bostrom argues that at least one of these three propositions must be true. If the first two are false, that is, if advanced civilizations routinely survive and enjoy running simulations, then over time, the number of simulated realities and the beings within them would become immeasurably greater than the number of base realities and their inhabitants. And if that is the case, then by the simple law of probability, any randomly chosen observer, such as you or I, is overwhelmingly more likely to be simulated than real. This is a purely logical deduction. It doesn't prove we are simulated, but it shows that this possibility must be taken seriously. The concepts of digital physics, the idea of space-time being pixelated, and the notion of the laws of nature functioning as algorithms all serve as circumstantial evidence that fits perfectly within the framework of this hypothesis. Beyond Nick Bostrom's purely philosophical argument, there are other, more physical considerations that strongly suggest we might be living in a simulation. One key factor is what's known as the fine-tuning problem of the universe. The core issue is this: fundamental physical constants, like the gravitational constant, the electron charge, and the speed of light, possess values precisely tuned for the existence of complex structures, and ultimately, life itself. If even one of these constants were slightly different, the universe would be unrecognizable. Stars wouldn't ignite, heavy elements wouldn't form, chemistry wouldn't exist, and therefore life as we know it would be impossible. Why is the universe so perfectly calibrated for our existence? There are several competing explanations. Some people attribute this perfection to the hand of a creator. Others cite the anthropic principle, We only observe a universe like this because we couldn't possibly exist in any other. A third major theory is the multiverse, which posits an infinite number of universes with varying laws and constants, and we simply got lucky to find ourselves in a hospitable one. However, the simulation hypothesis offers a strikingly simple alternative. The constants are so finely tuned precisely because a programmer set them that way. The simulation's creators merely chose the parameters of their virtual world to allow for the emergence and evolution of complexity. It's comparable to a game developer tweaking the physics engine settings to ensure the game is engaging and playable. Another compelling argument is the very intelligibility of the universe. Why is our physical world so perfectly described by the language of mathematics? How is it that we, creatures who evolved purely for survival on the African savanna, are capable of grasping the complex laws of quantum mechanics and cosmology? Perhaps it's because the universe itself is fundamentally built upon mathematical and logical principles, just like any computer program. It was likely created with the expectation that it could be understood, at least up to a certain predetermined threshold. If we truly are living in a computer simulation, the natural question is, can we actually test this? Can we uncover the telltale bugs in the code or glitches in the matrix that would expose the artificial nature of our reality? Some scientists believe this is possible. They suggest looking for anomalies and inconsistencies within the data gathered from our physics experiments. For instance, if our space-time isn't a continuous entity but a discrete grid, as is often hypothesized, this structure should impose specific limitations on physical processes. Theoretical physicist Silas Bean hypothesized that such a grid should lead to anisotropy, meaning that physical properties would depend on direction. Specifically, extremely high-energy particles known as cosmic rays would not travel identically across the grid in every direction. Their spectrum should exhibit a specific cutoff or limit, which would correspond directly to the cell size of this universal lattice. So far, no such effects have been observed, but the search continues. Another approach is to look for artifacts or rounding errors within the simulation's mechanics. Every computer, no matter how powerful, operates with limited computational precision. Perhaps at a very subtle level, we could detect that the laws of physics aren't working with perfect accuracy, but instead show slight deviations caused by these inherent computational errors. A third possibility involves searching for a backdoor or a hidden message left by the creators. If the simulation was built with a specific purpose, its designers might have included some kind of Easter egg, a discoverable signal intended just for us. Of course, all of this remains firmly in the realm of hypothesis and speculation. It's entirely possible that the simulation is so perfect that we cannot, in principle, distinguish it from base reality while trapped inside it. But the mere possibility of this search forces us to look at the world through completely different eyes, transforming every experimental physicist into a potential detective hunting for the fingerprints of the great programmer. When we delve into the idea of a computational universe, we inevitably confront one of the most complex and mysterious questions: the nature of consciousness itself. What is consciousness? Where does our self come from, our subjective sense of being, our ability to feel, think, and experience? If everything around us, including our bodies and brains, is part of a giant computation, then where does consciousness fit into that scheme? Is it simply the result of complex calculation? This perspective, known as computational functionalism, suggests that consciousness isn't a property exclusive to some special living matter. Rather, it's a property of a specific type of information processing. The physical substrate doesn't matter, whether the process is running on biological neurons in a brain or silicon transistors in a computer. If the system executes the correct computations, if it can model itself and the surrounding world, then consciousness will emerge. From this viewpoint, our consciousness is essentially a high-level operating system running on the hardware of our brain. It processes sensory inputs, builds models of reality, and makes decisions. Our self is an emergent property of this incredibly complex information system. Logically, this means it should be possible to create an artificial intelligence with a consciousness indistinguishable from our own. However, there is a powerful counterpoint. Figures like the physicist Roger Penrose argue that consciousness simply cannot be reduced to computation. They claim that our brain operates via non-computable mechanisms, potentially linked to subtle quantum processes within the microtubules of the neurons. From their perspective, human thought, especially intuition and creativity, cannot be simulated by a conventional computer or even a quantum one. If this hypothesis holds true, it fundamentally challenges the idea that we are merely characters within a simulation. Perhaps our consciousness is the very thing that connects us to base reality, a bridge between the computable world and something far greater. Intricately linked to the problem of consciousness is the ancient question of free will. If the universe truly is a giant computer governed by deterministic laws or probabilistic ones, if we consider quantum mechanics, does that leave any room for genuine free choice? Are all our decisions, thoughts, and actions simply predetermined outcomes of the universe's initial conditions and its governing algorithms? This age-old philosophical dilemma takes on a renewed significance when viewed through the lens of the computational hypothesis. If the universe is a purely classical, deterministic machine running like clockwork, then the answer seems clear: there is no free will. Everything, including the activity in our brains, is an inevitable consequence of the previous state. The future is essentially written already. Theoretically, we could compute it entirely if we knew the system's complete state at any given moment. Our sense of having choice is, therefore, just an illusion. We simply remain unaware of the cascade of causes that drive our actions. Quantum mechanics, with its inherent element of fundamental randomness, appears to offer a potential loophole for free will. If the outcome of a quantum measurement is genuinely random, perhaps our future isn't strictly predetermined after all. Some theories suggest that consciousness itself might somehow influence the outcome of these random quantum events in the brain, subtly guiding our decisions. However, most physicists and philosophers agree that simple randomness is not the same as genuine free will. If our decisions are merely the product of rolling quantum dice, that doesn't make us free. It just replaces rigid determinism with unpredictable chaos. The issue takes on yet another dimension when viewed through the framework of Stephen Wolfram's model of computational irreducibility. According to this model, even if a system is fully deterministic, its behavior may be so complex that predicting it is impossible faster than the system evolves itself. In this practical sense, our future remains open and unpredictable, even if it is theoretically predetermined. Perhaps our concept of free will is found precisely within this computational complexity, this practical unpredictability of our own thought processes. A fundamental concept in the theory of computation is the Church-Turing thesis. Essentially, it states that any problem solvable through an algorithm can also be solved by what's known as a Turing machine. The Turing machine, invented by Alan Turing, is a deceptively simple, abstract model of computation. It consists only of an infinite tape divided into cells and a read-write head that follows a specific set of rules to read, write, and move across the tape. Despite this basic structure, the Turing machine is universal. This means it can simulate any other computer, from the simplest calculator right up to the most powerful supercomputer. The Church-Turing thesis, therefore, defines the theoretical limits of what is fundamentally computable. If we accept the idea that the universe is a computer, the natural next question is it a Turing machine? Does reality itself adhere to the Church-Turing thesis? Most scientists working in the field of digital physics firmly believe the answer is yes. They hold that all universal processes are algorithmic and can, theoretically, be simulated on a universal computer, though the time and memory required might be unimaginably vast. This is known as the strong Church-Turing thesis, specifically applied to physics. If this hypothesis holds true, it implies that there are no magical or non-computable processes inherent in nature. Everything, from the evolution of life to the functioning of the human brain, fundamentally boils down to the processing of information according to defined rules. However, there are alternative viewpoints. Some researchers hypothesize that the universe may harbor what is called hypercomputation, processes that inherently exceed the computational limits of the Turing machine. These processes could potentially solve problems deemed strictly unsolvable by a regular computer. Candidates often cited for this capability include certain aspects of general relativity, like the possibility of time travel or quantum effects that we don't fully understand yet. Proving the existence of hypercomputation in nature would be revolutionary. It would mean our universe is running on a computer vastly more powerful than anything we can currently conceive. Let's revisit the fascinating concept of the universe as a giant quantum computer. We've discussed how elementary particles act like qubits, existing in a superposition of states. But how exactly does this computation happen? How does the universe process all this quantum information? One perspective is that the entire evolution of the cosmos, from the Big Bang to the present day, is essentially one massive quantum algorithm. Schrödinger's equation and other fundamental quantum physics laws describe how the universe's wave function, its total quantum state, changes over time. This can be visualized as the reality-composing qubits undergoing a sequence of quantum logical operations. With every tick of Planck time, the universe executes another step in this global calculation. What exactly is it computing? Perhaps it's simply computing itself. Its sole purpose might be to evolve according to its own internal rules. But there are more exotic hypotheses. For instance, some scientists propose the universe is solving some incredibly complex computational problem. We, with all our interactions, might simply be a byproduct of this massive calculation. This is similar to electrical currents running across billions of transistors inside a processor executing a complex program. The currents themselves have no inherent goal, but their collective action solves the task at hand. Another interesting concept is quantum Darwinism. This suggests that the stable, classical states we observe around us are the result of a kind of natural selection operating at the quantum level. Out of the vast diversity of potential quantum states, only those most resilient to environmental interaction survive. The environment constantly measures the system, effectively copying information about it, and only the most fit, the most easily and frequently copied states become objective reality. Thus, our classical world emerges from quantum chaos through an information processing mechanism that strongly resembles Darwinian evolution. If the universe truly is a computer, it must have a starting point and eventually an end point. That beginning is the Big Bang, the precise moment, computationally speaking, when the program was initiated. The initial state of the universe was astonishingly simple, hot and dense, characterized by incredibly low entropy. Think of this low entropy state as the initial dataset loaded into the computer right before processing began. But what about the conclusion? According to current cosmological models, the most probable scenario is the so-called heat death of the universe. Due to relentless expansion, the cosmos will become progressively colder and emptier. Stars will burn out, matter will decay, and even black holes will eventually evaporate. Ultimately, the only thing left will be a uniform, frigid soup of elementary particles and radiation, a state where all activity has ground to a halt. Temperature will be uniform everywhere, leading to a state of maximum entropy or ultimate disorder. From an information science perspective, this signals the end of all computation. Calculations are only possible when a difference, a thermodynamic gradient, exists between an ordered and a disordered state, between low and high entropy. This necessary gradient allows for work to be done and information to be processed. When the entire system settles into equilibrium, the computation ceases. The computer effectively freezes in its final, unchanging state. In this sense, the entire history of the universe, from its highly ordered birth to its chaotic demise, can be seen as one long computational process. This process systematically consumes its primary resource, low entropy, to generate complexity, create structures, and ultimately produce information. Heat death is the moment when the universe's hard drive runs out of operating space and the processor shuts down due to the lack of usable energy. It is a somber yet perfectly logical conclusion for our cosmic computer, one that fully adheres to the second law of thermodynamics, which, at its core, governs the irreversible growth of disorder within a closed system. One of the most fascinating aspects of our world is its sheer mathematical nature. Why do the laws of nature lend themselves so perfectly to the language of mathematics? How is it that elegant, abstract mathematical formulas, conceived purely by humans, can so accurately predict the behavior of physical objects, from a falling apple to the merger of black holes? This question has puzzled scientists and philosophers for centuries. The physicist Eugene Wigner famously captured this mystery in his essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." The computational universe hypothesis offers a very direct and logical answer to this enigma. The universe is so well described by mathematics precisely because, at its core, it is a mathematical structure. The laws of physics aren't just a description of reality, they are reality itself. They are the algorithms by which the cosmic computer operates. And mathematics is simply the language in which these algorithms are written. This worldview immediately raises another classic philosophical question. Is mathematics discovered or invented? Are we uncovering pre-existing mathematical truths, like Platonic ideals? Or are we inventing them ourselves, much like the rules of chess? From the perspective of a computational universe, the former is likely true. Mathematical structures and laws exist independently of us. They are the assembly language, the basic programming code, of our reality. We, as physicists and scientists, are akin to reverse engineers. We study the operation of this complex device, the universe, and try to determine the underlying source code, the foundational program, based purely on its observed behavior. Every new physical law we discover, every confirmed theory, is simply another line of code or function that we have successfully decompiled. This also explains why purely mathematical research, which sometimes seems utterly detached from reality, suddenly finds crucial applications in physics. By exploring the world of abstract structures, mathematicians are essentially stumbling upon the very building blocks from which the code of our, or any other possible universe, can be assembled. We are surrounded by astonishing complexity, from the intricate patterns of a snowflake to the billions of neurons in the human brain and the countless stars spread across galaxies. How did this complexity emerge from the simple, nearly homogeneous state of the universe shortly after the Big Bang? This process, known as emergence, is one of the central themes in modern science, and computational theory offers us powerful tools for understanding how it works. We have previously touched upon Stephen Wolfram's cellular automata, which dramatically illustrate how extremely simple rules can give rise to profoundly complex behavior. This is the core of emergence in the computational world. Complexity isn't pre-programmed into the system. It doesn't require a master plan or a blueprint. Instead, it self-organizes simply through the repeated application of those basic rules. Consider a flock of birds, a murmuration. Each individual bird follows just 3 simple rules: align its direction with its neighbors, maintain a certain separation, and avoid collision. There is no single leader orchestrating the movement. Yet these simple local interactions give rise to the complex coordinated behavior of the entire flock, which moves as a single, unified organism. This is the classic signature of an emergent system. Complexity theory, which analyzes these phenomena, suggests that our universe may be fundamentally tuned to operate at the edge of chaos. This is a state where a system is neither entirely ordered and static, nor entirely chaotic and unpredictable. It is precisely at this boundary that the most interesting and complex structures emerge, those capable of storing and processing information, leading to self-organization and adaptation. Life itself is perhaps the most profound example of this phenomenon. It harnesses the laws of physics and chemistry to build ever more complex informational structures, focused entirely on survival and replication. From a computational perspective, the evolution of life is effectively a massive search algorithm that explores the vast space of possible configurations, continually finding those that are the most stable and efficient at processing both information and energy. If the universe is a computer, does it face the same fundamental limits that constrain our own devices? In the 20th century, the mathematician Kurt Gödel proved his 2 famous incompleteness theorems, which profoundly shook the foundations of mathematics and logic. The first theorem states that in any sufficiently complex and consistent formal system, such as arithmetic, there will always be true statements that cannot be proven or disproven within the system itself. They essentially lie outside its boundaries. The second theorem shows that such a system cannot prove its own consistency. These theorems impose a fundamental limit on what formal logic can achieve. Alan Turing later demonstrated a strong link between provability and computability. Specifically, he proved the existence of the infamous halting problem. There is no universal algorithm that can take any arbitrary program and its input and determine whether that program will eventually finish or run forever. These results have profound philosophical consequences for physics, especially if we accept the hypothesis of a computational universe. If the laws of physics constitute a formal system, then Gödel's theorems might imply the existence of physical truths about our universe that we can, in principle, never deduce from those laws. There could be physical phenomena that are simply undecidable. The halting problem, in turn, suggests that we may never be able to create a universal predictor of the future. There would be no theory of everything that would allow us, given the initial conditions, to predict with absolute certainty whether any physical process, for instance, the formation of a black hole, will halt or continue indefinitely. These limits to knowledge may not be a mere reflection of our intellectual shortcomings, but rather a fundamental property of the computational nature of reality itself. It's crucial to note that while the hypothesis of a computational universe is certainly elegant and intriguing, it is far from being a universally accepted scientific theory. It's better viewed as a research program, a collection of ideas and metaphors that encourages scientists to approach established problems from a radically new perspective. However, this hypothesis faces serious criticism and unresolved challenges. One of the biggest obstacles is bridging the gap between the discrete and the continuous. While quantum mechanics has achieved tremendous success, many foundational areas of physics, especially general relativity, which describes gravity and the structure of spacetime, are still fundamentally based on continuous mathematics. To date, no one has succeeded in developing a completely discrete theory that accurately reproduces all of Einstein's predictions. How exactly does the smooth, observable geometry we see at the macro level emerge from discrete pixels of spacetime? That remains an open question. Furthermore, critics argue that the computer analogy might simply be a form of anthropocentrism. We have a historical tendency to explain the world using the most cutting-edge technology available at the time. In the 19th century, the universe was compared to clockwork machinery. Today, we liken it to a computer. It's plausible that a future technological breakthrough will yield an entirely new, more compelling metaphor. Fortunately, there are alternative approaches to developing a theory of everything that do not depend on the computation framework. For instance, string theory proposes that the fundamental building blocks are not point-like particles, but rather tiny, one-dimensional strings. But the different vibrational modes of these strings are what we perceive as different particles. Another approach, loop quantum gravity, attempts to quantize spacetime itself, modeling it as a network of interconnected loops. While these theories also embrace discreteness at the Planck scale, they don't place the same strong emphasis on information or computation. It is entirely possible that the final theory will ultimately unify elements from all these different approaches. Science is an ongoing process, and we are still only at the very beginning of our journey toward understanding the fundamental nature of reality. Despite inherent complexities and ongoing criticism, the notion that information is the fundamental building block of the universe is becoming one of the most powerful concepts in modern physics. It offers a unifying language, a common framework that might finally connect the two greatest theories of the 20th century, general relativity and quantum mechanics. Each of these theories works perfectly within its own domain. General relativity accurately describes gravity and the macroscopic world of large scales, while quantum mechanics governs the microscopic world of atoms and particles. But fundamentally, they are incompatible. They rely on different mathematical frameworks and produce contradictory predictions when applied to extreme environments where both quantum and gravitational effects are dominant, such as the singularity of a black hole or the very first moment of the Big Bang. The quest to create a single, unified theory of quantum gravity is the central challenge in theoretical physics today. And the information approach may just be the critical key to unlock this unification. We have already seen how the study of information within black holes led to the holographic principle, which fundamentally links gravity to quantum field theory. Many physicists now believe that space-time itself is not fundamental. Rather, it is an emergent phenomenon arising from a deeper structure, the intricate interweaving of quantum information. Imagine that space is a kind of illusion generated by the correlations and entanglement between the fundamental qubits of reality. The very geometry of space-time, the curvature we perceive as gravity, is merely a manifestation of the underlying structure of these information linkages. In this worldview, both general relativity and quantum mechanics are simply different approximations, different ways of describing this single, profound quantum informational reality. The search for this fundamental theory is essentially the search for the universe's ultimate source code. Let's take a step back and look at the big picture. We started with a simple analogy. The universe is like a computer because it processes information according to specific rules. We then saw how this seemingly simple metaphor finds confirmation across various fields of physics. We looked at the concept of discrete, pixelated space-time at the Planck scale, the quantization of energy and other physical quantities, the holographic principle, which suggests that our three-dimensional reality might be a projection of information stored on a two-dimensional surface, black holes serving as nature's most effective storage and processing units for information, conservation laws, viewed as the invariance of the cosmic program, and the speed of light, its ultimate clock speed. We considered quantum mechanics as the description of a colossal quantum computer, where particles are the qubits, and entanglement is the non-local connection within the code. Even complex phenomena like the emergence of complexity and life itself are explained within the framework of computation theory and emergent systems. This concept offers a unified and coherent view of the world. It prioritizes not matter and energy, but a more abstract and, arguably, more fundamental entity, information. It transforms the laws of physics from mystical rules imposed upon the world from the outside into the inherent properties of the operating system itself, its algorithms. It provides us with a new language and new tools to explore the deepest mysteries of existence. Of course, this doesn't mean we have figured everything out. On the contrary, this worldview generates even more questions. But these are good questions. These are the questions that drive science forward and force us to fundamentally rethink our most basic assumptions about what reality truly is. So this brings us to the final and perhaps most difficult question. If the universe is a computer, if our reality is indeed a simulation, then who hit the start button? Who wrote the program? This question immediately takes us beyond the boundaries of physics, plunging us deep into the realm of metaphysics and philosophy. Science, by its very nature, studies the program itself, its rules, its structure, its behavior. It simply cannot look beyond the screen to see the programmer. Any answer we offer here must reside in the domain of belief or pure speculation. One possibility is that the programmer was some highly advanced civilization operating out of a base reality, echoing Nick Bostrom's simulation argument. Perhaps they launched our simulation for research, historical reconstruction, or even purely recreational purposes. To them, we might be nothing more than an immensely complex video game or a scientific experiment. Another possibility is that our universe is part of an infinite hierarchy of simulations. We are simulated by one civilization, which is in turn simulated by another, and so on, either indefinitely or until we reach some fundamental, true base reality. Yet another, more abstract idea suggests that the universe is a self-organizing, self-calculating system. There is no external programmer. It generated its own laws and structure through a process we might call cosmological natural selection. Perhaps there is a multitude of universes, and only those whose laws permit the existence of complexity and observers, like us, are the ones that survive. Finally, this question inevitably resonates strongly with traditional religious and theological concepts of a creator. The idea of a God programmer who designed the world by writing its fundamental code is an incredibly modern notion and one that many find compelling. Ultimately, we don't have an answer, and perhaps we never will. But the question itself forces us to reflect on our place in the cosmos and the fundamental meaning of our existence. Are we merely the random product of blind laws of nature? Or are we part of a grand design? Are we fundamental reality? Or are we simply shadows on the wall of Plato's cave, projected from a world of a higher order? Our long and thoughtful journey into the hypothesis of the computational universe is now drawing to a close. We've established that this idea isn't mere science fiction. It's a serious scientific paradigm that effectively merges concepts from physics, computer science, and philosophy. This paradigm suggests viewing reality through the lens of information and computation. Let's recap the key elements of this worldview. The universe behaves like a computer because it processes information, the state of particles, using algorithms which are the laws of physics. At the most fundamental, Planck-level space and time might be discrete, pixelated, hinting at the digital foundation of reality. Quantum mechanics, with its principles of superposition and entanglement, makes the universe resemble a gigantic quantum computer. The holographic principle suggests that our three-dimensional reality could be merely a projection of information stored on a two-dimensional boundary. And finally, the simulation hypothesis pushes this logic to its absolute limit, proposing that our entire universe might be an artificially created program. This picture of the world might seem cold and mechanistic, appearing to strip the universe of its mystery and wonder. But in my opinion, the opposite is true. Recognizing that we might be part of a colossal, unimaginably complex calculation, one that has been running for nearly 14 billion years, infuses our existence with a thrilling new meaning. This realization doesn't diminish the beauty of a sunset or the complexity of human emotions. Instead, it only deepens our admiration for how elegant and powerful that fundamental program must be, capable of generating all this richness and intricacy from the simplest rules. Ultimately, it transforms us from passive inhabitants of the cosmos into active explorers, dedicated to deciphering its code. To conclude, it is essential to stress that the hypothesis of a computational universe is, above all else, a powerful intellectual framework. It provides us with a new language for describing the world, a language that proves to be surprisingly effective. Perhaps this hypothesis will eventually be disproved or superseded by a more advanced theory, or conversely, it might gain powerful experimental confirmation and become the very bedrock of 21st century physics. But either way, it has already changed our perspective on many fundamental questions. It has forced us to contemplate what information truly is and what profound role it plays in the structure of the cosmos. It has demonstrated how infinite complexity can emerge from ultimate simplicity. It has blurred the lines between the physical and the abstract, between matter and mathematics. And of course, it has presented us with the deepest existential questions. Who are we? Where do we come from? And what is the true nature of our reality? This hypothesis is a powerful reminder that the universe is far stranger, more wondrous, and more mysterious than we could ever imagine. It suggests that the greatest discoveries await us at the intersection of discipline, where physics meets computer science and science meets philosophy. As you drift deeper towards sleep, allow these ideas to flow freely through your mind. Imagine the universe as an ocean of information, where every wave, every particle is the result of a massive, eternal computation. And you are not merely a grain of sand in this ocean, you are a part of it, a part capable of realizing and attempting to comprehend the complexity and grandeur of the entire process. And in that act of realization, perhaps, lies one of the primary purposes of this cosmic computation. And here we are now, sitting in this quiet space, alone with a truly striking idea. The thought that the very fabric of reality is woven not from matter, but from pure information. That the space surrounding us might actually be composed of invisible pixels, and time itself flows in discrete Planckian steps. But the most stunning twist in this entire narrative is, of course, the holographic principle. This suggests that our three-dimensional, volumetric, tangible reality might be nothing more than a projection, a hologram, encoded on a distant, two-dimensional boundary. We might not actually be living inside the book itself, but rather just on its cover. This completely overturns our intuitive grasp of the world. And naturally, there's the simulation hypothesis, which transforms us from masters of our own destiny into characters within someone else's program, forcing us to reevaluate everything we once held to be real. The main takeaway from our journey is simple. Viewing the universe as a gigantic computer is much more than just a thought experiment. It's a fruitful scientific approach that is already helping us solve the most complex puzzles in physics, and may one day lead us to the long-sought-after theory of everything. Thank you for spending this time with me, sinking into these deep and restful reflections. I truly hope this session has helped you relax and prepare for a good night's sleep. If you enjoyed this journey into the depths of science, please give this video a like and subscribe to our channel so you don't miss future sleep lectures. Now, just before you drift off completely, let me leave you with one final question. Please write your answer in the comments when you wake up tomorrow morning. If you were granted momentary access to the source code of our universe and could change just one line, one constant, or one rule, what would you change and why? Good night, and may you have peaceful dreams of the calculating cosmos.